Kindly wait for some time for other people to join and then we will start the session. Okay, we can start today's live session. Um, good evening, everyone. So, today is the last live session or problem solving session for this course. If you have any queries regarding the course content, if you have any problem understanding any course content, you can ask me today and I will try to answer them. If I'm not able to give you a proper answer, then you can give me your mail ID and I will try to find out the answer and send the uh, answer to you by mail. And so, do you guys have any questions regarding any course content? Anything you do not understand? Any questions you have? No questions? Okay, so we are gonna start today's session then. Okay, so can you see the presentation? Is the presentation visible?
Yes.
Okay, thank you. So today is the last session, and we will be talking about a little bit about electrospinning, and then we will be talking about we will be talking about 3D bioprinting. Just a little overview. You have already studied 3D bioprinting. Just I'll be giving a brief overview about the entire process of 3D bioprinting, how it is done. Okay, so electrospinning. So you guys have studied electrospinning till now. I think you might have already studied electrospinning till now. So what is electrospinning mostly used for? Electrospinning, what is it used for? Nanotubes. No, I'm sorry. No, it's wrong. It's not nanotubes. Nanotubes is like carbon nanotubes that is formed by chemical vapor deposition, CVD. Electrospinning. What will you form by electrospinning? Fibers. Yes, correct. Now you're correct. Nanofibers. So, what is the use of the fibers? What application can you have of for fibers? Nanofibers. Like, why is electrospinning important? Framework for cell biology. Basically, you have to make a scaffold. So, if you want to do tissue engineering, so you need a scaffold on which your cells will be seeded and it will grow. So, that will be provided by your nanofibers. So electrospinning is a very useful and efficient technique to produce ultra fine polymeric fibers. So it has outstanding properties, make the polymer nanofibers to be good candidates for many applications which extend to filtration, tissue engineering, wound dressings, protective clothing, drug delivery, cosmetics, electronic and semiconductor materials. So basically you can make nanofibers and you can have so much of applications. You can make a filtration unit out of a nanofibers. How will it work as a filtration? How can it work as a filter? Any idea how it can work as a filter? Any idea how it can work as a filter? Yeah, acting as molecular sieve. You're correct. So, acting as molecular sieve, then what do you need to regulate? The pore size. So you have to regulate the pore size in such a way, like you have to synthesize your nano fibers in such a way that your pore diameter is fixed. Okay, so you have a particular size of particular pore diameter nanofibers, then only it will act as a molecular sieve. Yes, you're correct. So that is how you can do filtration. Tissue engineering, we all know that nanofibers are very good material for scaffold, and on scaffold you will seed the cells, provide your growth factors and everything. So basically, your scaffold will act as a ECM, extracellular matrix, for tissue engineering, on which your cells, seeded cells, will grow. Wound dressings, this is also very nice application of nanofibers. Wound dressing, basically what happens is that you make a patch with nanofiber in which you load your drug, so that when you are like we have the problem of like when you apply a band-aid on a cut then what happens when you're peeling the band-aid off, you feel some pain. So nowadays what scientists and researchers they're doing, they're making dressings, wound dressings, having your either the wound dressings will have some kind of nanoparticles, be it silver nanoparticles. You know, silver nanoparticles have antibacterial properties, right? You know this? Silver nanoparticles have antibacterial property.
Yes, yes, we are using it in dressings.
Okay, yeah. So, so basically, yes, correct. So, basically, so for wound dressings, sometimes what will happen is you will make a nanofiber and you will incorporate silver nanoparticles in the in between the nanofibers, so that it will act as an antibacterial, and you will be using a polymer which will be not which will be adhesive, but it will not hurt you when you're peeling it off. It will not hurt you. Okay, so that kind of wound dressings are currently being developed by scientists and researchers, and you can also load drugs. Suppose you want to cure a disease, so like even for cancer therapy, sometimes there are some places where your drug is not able to reach, or maybe cannot stay in the system for a long time. So that your drug is released in a slow manner, like slow release of the drug happens. So for that also nowadays patches or bandages are being made with nanofibers, in which you're loading the chemotherapeutic drug, and then you are putting the patch on the cancer patient at the site where the tumor is, and the patch is such that it will be slowly degraded and it will slow release the drug. Okay, so that is more effective because your drug will be slowly released and it will slowly be acting on your patient. Okay. So that is another. Then protective clothing, drug delivery, already said one example of drug delivery, how you can do drug delivery. Cosmetics also, nanofibers are used. Cosmetics, actually, a lot of nano emulsions and liposome mediated nanoparticles you will see mostly in cosmetics. If you follow some ads, especially foreign brand ads, you will see mostly the foreign brands, they will say that some nanotechnology based cosmetic products are made, and they use nano emulsion technology, some pore technology. Someone, okay. Another in cosmetics, one thing is very is used very often. Do you know what it is? Like a cosmetic for anti-aging. So cosmetics which, or health or skincare products which boast that they have anti-aging properties. Do you know what they have? Yes, yes. Face mask is a type of cosmetic. No, not collagen. They have telomerase. So they will be having an enzyme which mimics the telomerase, so that with age your telomerase doesn't like your telomeres don't shorten. What happens is that with age your telomeres will shorten each time, right? That is why your cell undergoes senescence. So in to increase, so that you remain young, what those skin products or cosmetics, what they have is they have a component called telomerase, and that will, protect your skin. That will not shorten the telomeres in your cells. As a result, your cells will keep regenerating, they will not undergo senescence, and you will remain young. But do you know one disadvantage of that? That's the advantage, that you can remain young, your telomeres will not shorten. But disadvantage of that?
Cell clearance, the normal cell clearance of the skin, which should take continuously, will not take place in
Yes,
its
that.
natural time.
Yes, natural processes will be affected, and apart from that, if you apply it or use it too much, then what can happen is that since your telomeres are not shortening, your cells are continuously dividing, you can develop cancer. So too much of anything is not good. It's a natural, aging is a natural process. You're trying to stop it, so it will affect something or the other in your body. So that is also one example. Then electronic
Can
enzyme.
telomeres not break the chromosome?
Uh, Telomeres, the end of the chromosomes.
The end, I know, because they are blocked ends, right? So that they don't open up at the end
Yeah,
of the chromosomes.
yeah. They're
Yeah.
heterochromatin.
So, mm,
So they are not
so,
replicated. No, every time a cell replicates, that is not replicated. So every time you lose some part of it.
huh.
That is known as
Okay, okay.
telomere shortening.
Mm-hmm.
Hmm.
Which defines the age of the cell.
Yeah. So your question
So
was?
telomerase and the telomerase enzyme,
Hmm.
is it possible for, like, when used in a higher quantity,
Hmm.
which natural acting of telomerase, won't it affect the telomerase? Um, how can I explain this? Normally, enzymes are used to break. There are multiple processes which are controlled by enzymes, whether it's
Yes.
synthesis, breaking down, or transformation, depending
Yes.
on its requirement. So, for
Yes.
this telomerase, what is its actual activity at that specific instant?
So basically, your telomeres will be replicating your telomeres. Right,
Okay,
that is the action of your telomerase. So it prevents the shortening of the it will protect the telomere and it will prevent its shortening. That is the work of telomerase.
so
Okay.
if it replicates, it requires to get incorporated within the chromosome, right? Won't that confuse the cell?
No, it's already part of the chromosome. Your telomeres are already part of your chromosome. Only thing is that it's not euchromatin. It's heterochromatin. It is silenced always. It's not replicated.
Okay, okay.
Okay, so you have two types of chromatin in your DNA, right? Euchromatin and
Yeah, yeah.
heterochromatin. Euchromatin is the portion which is undergoes transcription translation, and heterochromatin are the silenced areas. Your telomeres are heterochromatin; they are silenced areas. So whenever you need to replicate it, the telomeres will act on it and replicate it.
Oh, okay, okay,
Okay, so
okay, got it.
the telomeres will do it. If you lack that, then your telomeres will not be replicated and it will undergo shortening. With that is why, since it's not being replicated, with each cell replication, your like telomeres will keep shortening, and that's how you are losing information, and slowly the cell undergoes death.
Okay, okay,
Okay,
okay.
did you understand?
Yeah, yeah.
Okay. So, coming back to electrospinning, so it is versatile, cost effective, and has the potential to be used in a wide range of applications, resulting in an outstanding potential for nanotechnology research. So, this electrospinning is a very powerful tool because I guess you already have studied other ways of synthesizing nanofibers, but electrospinning is the most easiest and you can say to fabricate nanofibers, and you will get very fine nanofibers depending on your conditions, what conditions you're using. Did anybody ever use electrospinning or have seen an electrospinning apparatus? Ever used electrospinning?
Is it a nanospin machine? There is a name of nanospin machine in my lab.
It will
Is
be
it the
written
same thing?
e-spin, it will be written on the machine.
Okay. I haven't used it, but I've seen PhD
it's it's
scholars
a it's a
using it.
it's a very big instrument, and it will have your holder for your syringe. It will have your collector space, either your plate collector or your drum collector you have to attach separately. We
And
use
then there
plate.
is some kind of a specific fluid which you provide inside and which throws towards the opposite side
Yeah,
of the
your
screen.
fluid will be polymer. It will be a
Ah,
polymer.
polymer, yeah.
Yeah, based on the type of work you're doing, based on your application, you are going to be choosing a polymer. So that polymer will be, the polymer will be pulled into strings, which will form your nanofibers at very high voltage.
Yeah, 50,000 voltages it was
Yeah.
stated, I guess.
Yeah. So very high voltage. So we will be talking about how it is forming. Like if you're having a polymer solution, how is it that it is forming fibers, right? That comes. Even if you apply voltage, how will it form fibers? There has to be a mechanism for it to form fibers. So we will be discussing that in short. Okay. So what is electrospinning? Electrospinning is a fiber production A method which uses electric force to draw charged threads of polymer solution, or polymer melts up to fiber diameters in the order of some 100 nanometers. So your nanofibers will be which kind of material? 0D, 1D, 2D, 3D, which kind of material? Nanofibers will be which kind of material? 2D, yes. 2D, no, you're wrong. Sorry, not 2D. What kind of material will be nanofibers? Think about it a little bit more. What is 0D? What is 1D? What is 2D? What is 3D? What kind of material will be 1D? Yes, correct. Why 1D? Because only its diameter is in nano dimension. Otherwise, your fibers are in meter lengths. It could be in meter lengths. Okay, it could be very, very long. It like you can get continuous fibers also, no? So it could be very big in length. Length will be micrometer range, but more than nanometer range. Only your diameter of the fibers are in nano range. That is why it is 1D. 2D, always remember 2D materials are like sheets, like graphene, graphite, graphene oxide, reduced graphene oxide, anything which form films are 2D. So basically sheets will be like 2D. And 1D are tubes, carbon nanotubes. Like if you get dots like quantum dot, carbon dot, then 0D. And bulk material is just normal 3D is bulk materials. Is it clear? Don't get confused by this. What kind of material 1D, 2D? Like if you are asked to categorize, suppose no. Only the diameter. Only the diameter. You should consider only the diameter, not radius and length. Length will definitely be very big. Only the diameter should be considered. For a circular thing, like if you have a tube, only consider the diameter. Okay, radius will be half of the diameter. No, so you should consider the entire diameter. Um, so because you could be asked questions like this, if suppose you're asked a question like this, then you should be able to answer what kind of material is 1D, what kind of material is 2D, what kind of material is 3D. Okay, so don't get confused. Just think about what kind of dimensions they have, and then you answer it. Okay. So this is what is electrospinning. So basically what you're doing, you're taking a polymer solution and then you're charging it. You're applying a charge to it. So your polymer solution has to have some conductivity. So non-conductive polymers will be very difficult to spin because non-conductive polymers will not have any charge. Okay, so you need to have some kind of charge in order to spin the polymer into a fiber. Okay, so you have to have some electric force to draw charged threads of polymer solution. Okay, so what is electrospinning? Here you can see how it is forming. So why we are calling it electrospinning? Because mainly you see two mechanisms are used. One is you use high electric voltage, and another is you're spinning of the polymer to form fibers. That is why it's called electrospinning. So how we are spinning the polymers? If you have a plate collector, then you are not spinning the polymer. So basically your plate collector will directly collect your the plate collector will directly collect your nanofibers in random directions. But if you have a drum collector, then the drum will be rotating and you will be collecting your nanofibers in a particular direction. Okay, so it will be arranged. Nanofibers will be arranged in a particular direction. So here you can see in the picture that this is the tip of the needle. Okay, and here you can see your polymer solution droplet. So spherical droplet, when it forms a spherical droplet, there is only surface tension. Okay, so your surface tension of your polymer solution is also very, very important, because depending on your surface tension, it will form a very fine Taylor cone. Here you can see in the later images that the polymer droplet from spherical, it is forming a cone shape. Okay, this cone is very important. So what happens when you put electric charge, like you're putting charges on this needle and your collector. There is a charge difference between the needle and your collector. Then what happens? You have surface tension plus localized charges. So your surface tension is more compared to your localized charges. Okay, so when this Taylor cone forms, that means your surface tension and localized charges are equal. And as soon as your localized charges is more compared to the surface tension, then what will happen? From this Taylor cone, very fine polymer solution will be coming out, that will form your fiber. So that fine polymer solution, this line that you can see, that is your fiber coming out. So this will only happen when the surface tension of your polymer solution is less compared to the localized charges. Okay, so here you can see that more electric charges being given, more charges are accumulating, and it is forming a Taylor cone, and then your fiber is being spin out from this Taylor cone. Understood how this Taylor cone formation happens? This is very important, Taylor cone formation for electrospinning. Another thing that you should always notice, uh, any questions? Did you understand Taylor cone formation? Okay, so another thing that you should keep in mind, as you can see here, that the needle tip, here you can see it is flat, but usually the needles that firstly you have to use a needle which is like sterile, so and not used for any other purposes. So what we do is we take syringes, and we'll take the needle from the syringes. So you're already using a syringe to put, so that syringe will have a needle, but that needle, you know, it is not flat, right? That needle is slanted. It has a very sharp tip. It is slanted. It is cut in a slant way. So the first thing that you have to do is you have to cut your needle so that it becomes flat. If you forget to cut your needle, this is one precaution you should always maintain while electrospinning. That is, if you forget to cut your needle and your needle is slanted like this, then it will form a deformed spherical droplet, and your Taylor cone formation will not be correct, and your electrospinning fibers will all be of different diameters, different, the surface tension, like every mechanism will work differently. Okay, so for that, first thing you need to do is you have to cut the tip of your needle so that it is plain, straight. Then only you can put your polymer solution and extrude it under high voltage, high electric voltage, and you will get your fibers. Okay, this is a precaution you should remember. Then we are having so nanofibers. What are nanofibers? These are basically fibers with the diameter in the nanometer range. So you can make nanofibers from different polymers, like you can use natural polymers like collagen, cellulose, silk, fibrin, keratin, polysaccharides, chitosan, and alginate, and synthetic polymers like polylactic acid, polycaprolactone, polyurethane, and polylactic lacticoglycolic acid. These all can also be used. PVA, then what else? You can, yeah, PVA also you can use, polyvinyl alcohol. So all these kinds of synthetic polymers also you can use for your nanofiber formation. So if you are going for a biological application, the first thing that you should see is what kind of application it is. Suppose you have to make a scaffold on which what kind of cells you will grow. So if you need to grow a particular type of cell which requires collagen or keratin as its for its growth, then you can use these kind of natural polymers for your nanofiber formation. Similarly, for synthetic polymers, you can choose a polymer which is is biocompatible, so that if you're going for a biological application, it should it should not affect the body. So it should be biocompatible, especially if you're putting it inside. Okay, so this is the electrospinning process. So what is happening is you have mainly three components. First, you have a syringe with the polymer solution. So like I said, the needle of your syringe is very important, because that diameter will determine the diameter of your uh, nanofiber. So the smaller the diameter, more ultra fine fibers you will get. So this diameter of this needle is very important. Then high voltage supply. So the higher voltage you apply, the more finer Taylor cone you can see. The more finer Taylor cone will be formed, and with each and the more finer your Taylor cone is, the more finer your nanofibers will be. Then you have a metal collecting screen. So this here is shown as a drum collector. As you can see that this is grounded. Can you see it is grounded, the collector? So what will happen is that from this needle, the polymer solution will be pushed, extruded out of this needle under high voltage supply. So this is having some voltage, and this one is grounded. So this will generate some charge, and this will be neutral. So it will attract, if your polymer solution is charged, so it will attract your fibers towards itself, and it will be collected here. Okay, and here you can see that this is how it looks under SEM. So basically, after you have formed nanofibers, the first characterization you should do to see how well your nanofibers have formed is to do SEM. Okay, so this is a SEM image. This is not a drum collector image, because in drum collector I said that this random fibers will not be deposited. It will be deposited in a particular direction. So this one is a plate collector image. Okay. Sorry. Yes.
Uh, Having so much high voltage, won't it melt the tip of the syringe?
Uh, it is not touching the syringe.
So how is it passing the voltage
So
to the syringe?
basically you have a holder in which you're putting the syringe. Okay. So that holder will be charged. Your polymer solution will be charged. Okay. And it will not, definitely you are putting enough voltage that will charge your polymer solution. Basically aim is to charge your polymer solution so that it is pulled down. Okay, I will show you an example where you are using two kind of charge system. That example that I showed you here, your collector was grounded. Okay, there is another kind of charge system where your collector is also charged. So the charge distance, either your polymer solution is positive or negative, or your plate is of opposite charges. So that will pull the fibers down. It will attract the fibers down. Okay, so obviously it has a very high voltage. So usually after using the apparatus, what we do is we have a rod which discharges the charge. So you should also not forget that you should take that rod before touching anywhere in the instrument. After you have used it, you are supposed to remove that charge, or else you will get a very big shock. So you are supposed to take that rod and touch it, and that rod is grounded, so that charge will pass down to the ground, and remove any kind of charges, be it on the plate, be it on the side of the syringe, anywhere. You have to just touch it so that your charges are removed. So this is also precaution you have to take. Never forget to touch that. Never touch directly, or else you'll get a big shock.
Okay, got
Okay.
it, ma'am.
Okay. Um, so this is the procedure for electrospinning. An electrostatic potential is applied between a spinneret and a collector. What is a spinneret? Spinneret is basically this entire setup: your syringe, your needle, and the holder for your syringe, which will have a piston which will push this needle, push this syringe nozzle down. Okay, so that entire thing is called the spinneret. 1 second. So that entire thing is called a spinneret. That spinneret, so basically electrostatic potential is applied between a spinneret and a collector. So this is your collector, this plate you can see is the collector, and this is your spinneret setup. So there will be an electric voltage that will be applied, electric potential will be applied between your spinneret and the collector. As you can see here, your polymer is having positive charges and your plate is having negative charges. So as soon as your charge is the charge of your polymer solution is higher compared to the surface tension of the polymer solution, it will start extruding through the Taylor cone as fibers, which will be collected in your plate. Okay, so the fluid is slowly pumped through the spinneret. This fluid, this pumping is regulated by the flow rate. So you have to maintain a steady flow rate. The flow rate should not go up and down. If there is a difference in flow rate, then you will get different diameters of nanofibers. So your flow rate should be constant. So the fluid is slowly pumped through the spinneret. The fluid is usually a solution where the solvent can evaporate during the spinning. Okay, so basically you should put your solution in a solvent which can evaporate. Most of the time we dissolve it in water. You can use other solvents also. You can use some organic solvents also. Basically, it has to evaporate during the spinning process. The droplet is held by its own surface tension at the spinneret tip until it gets electrostatically charged. Like I explained for this Taylor cone thing, that it will form a droplet, it will have a surface tension of its own, and it will form a Taylor cone and eject the fibers, and when it has enough electrostatic charge to overcome its surface tension. The polymer fluid assumes a conical shape, which is called the Taylor cone, and when the surface tension of the fluid is overcome, the droplet becomes unstable and a liquid jet is ejected. So this liquid jet basically forms your fiber, nanofibers. So this is a setup of the electrospinning process. You can see two kinds of setup. One, you can see the spinneret is on top and your collector is at the bottom, and you have a voltage supplier at the side. Another setup you can see here on your right hand side is you have a syringe pump which will which will push the piston of the syringe down so that it ejects the polymer solution through the metallic needle. And this polymer solution and this is like horizontal, and your collector is here, metallic collector is here. So this first setup on your left, this is called a vertical setup, vertical electrospinning apparatus, and this is a horizontal electrospinning apparatus. So you can find both kind of apparatus. You can use either of them for the electrospinning process.
Ma'am,
Yes.
the fibers being so small, so their weight would also be less, right?
Yeah.
So when they are pushed under such a force of rotation, won't there be a loss of fibers when they are continuously rolled and sent towards the
Yes,
scaffold
yes,
area?
yes. A lot of fibers. Like if you're having, usually the plate is very big. What we do is we take the plate, you will cover it with an aluminium foil. Okay, you should remember you should not touch the inside of the aluminium foil with your hand. You should always use gloves, obviously, but you should not touch the inside of the aluminium foil. So it should be a fresh, untouched aluminium foil, and on the aluminium foil, basically you collect your fibers. Okay, and then you will take off the aluminium foil and slowly peel the fibers off the aluminium foil for your further analysis, SEM analysis or whatever. But what happens is that it's not like, even if your collector is so big, if you have a drum collector or if you have a plate collector, compared to the drum collector, your plate collector is bigger, but whatever collector you have, it's not like the fibers will only be formed on the plate. There are also fibers, because it has there should be no humidity, no air interference. That's why the entire setup is inside a closed chamber. So whenever the electrospinning is going on, you're not supposed to open the chamber. Whenever you open the chamber, you are supposed to stop the process or halt the process, and then you open the chamber. Whatever work you have to do, first Don't touch without discharging the charge. You have to touch with that rod, which is earth, so that the charge is discharged, and then you touch the apparatus and you close the door. Okay, so basically that fiber will be shifting here and there if there is some kind of air interference, because it's very light. But other than that also, sometimes what happens, this fibers will be spilling out on the sides, so that is very loss. Mostly it will be collected in your area where you're collecting, and whatever is being collected on the sides, that you have to clean after every run. So after using your instrument, you have to clean that after every run, so that your next person can use it fresh. So so
So can't
yes,
we
you
combine both? So can't we combine both drum and the largest area which is in front? Assume that the fibers are being sent towards the screen, which
hmm,
is in front of it.
hmm,
And in such a case, taking the concept of the drum, which is actually cylindrical,
hmm,
so it takes inside as an it takes inside the fibers.
hmm,
So now instead of the drum in front, I put a scaffold. Then I put a smaller scaffold on the top, on the sides, and on the below part, which is connected to each other. And the along with the electrospinning material, the this also rotates or stays stagnant. So it would reduce the loss. Is it feasible or it's not? Hmm.
you can do a lot of setups, but the thing is that basically what you need is an area of electrospun fibers. Mostly, if you're suppose if you're using a horizontal one, your needle is here, most of it will be collected just below the needle. That's the maximum place you will get your collection of nanofibers. Similarly, if you're
Hmm.
using a horizontal one, like you were saying, your screen is your like the screen is the direction where your fiber is going. So basically, that is the horizontal one. So this is your needle, and like 1 second. This is, yeah, so this is your needle and this is your collector. So it will also straight go and collect here. Very less is spilled on the outsides. They obviously there is some spillage, but very less. Okay, so if you want to minimize that, and if you want to attach something else so that even that spillage does not happen, that depends on you completely. But the collector is fixed. Like whenever you buy the instrument, they will give you maybe plate collector, drum collector. They can give you different sizes of it, but they will give you only collector, one collector. Okay, so they will give you only basically uh, one big plate collector and one drum collector. Some instruments can also give you different sizes of the drum collector and the plate collector. That depends on the company whether they will give or not. Usually they will give one of each, and then you have to basically spin and form the fibers. Also, wherever the polymer solution is coming out from, there also will be some drippage. Initially there will be some leakage of polymer solution before you apply the voltage, so that also you have to clean every time. If you do not clean that, that will drop and fall, and also it will form a big like nodule. If your flow rate is not constant, if you're not removing those big what do you call it, big droplets forming, then those droplets will also go and fall on your fibers, and it will form big nodules in between the fibers. Okay, those are something which is unnecessary. You do not need that in your fibers. So always try to take pictures of places where those nodule like things are not there. Yeah. So did you understand that you can do a setup like that to minimize your loss, but at the end of the day, basically you most of your sample will be collected in the center. So it depends on you that whether you want to prevent the loss or you want to let go of whatever little bit of sample loss is happening, and you can just clean it later. So that depends on you. Anyways, whatever you're collecting, you have to put aluminium foil. You have to paste an aluminium foil, and then you have to collect. Okay, so coming back to the electrospinning process, so electrospinning parameters. So these parameters are also very important because these parameters will affect your nanofiber diameter. So what kind of parameters? Basically solution parameters like viscosity, conductivity, molecular weight and surface tension. Okay, so these are certain solution parameters which will affect your fiber diameter, and process parameters like electric field, like how much voltage you're applying. Tip to collector distance. So your spinneret tip and your collector, if it is very close by, then after forming the Taylor cone, when your fibers are ejected, it will not, like, even gravity has some effect, right? So that gravity effect will not be too much, and you will get fibers with thicker diameters, bigger diameters. But if your tip to collector distance is more, then you will get more fine, because the jet which is ejected will become more fine as it reaches the bottom, and as a result, also due to some effect of gravity. So as a result, you will like combined effect of your electric voltage that you have applied as well as a little bit of gravity, and you will get more fine diameters. So the tip to collector distance is also very important. Flow rate, I said, is also very important process parameters. If your flow rate is not constant, you will form those nodules. I was saying those nodules will be formed. So basically suddenly you will see that it is ejecting liquid, it is ejecting the fiber in very fine stream, and suddenly you will see one drop of your polymer solution falling onto your collector. So that drop will basically solidify and form a big nodule in your fiber. So that you have to maintain so that you do not get drops along with your stream of nanofiber. Hydrostatic pressure, humidity and temperature. Temperature should not be too high, it should not be too low. Temperature should be enough to melt your polymer solution. Okay, so that you can eject it through the nozzle. So these are some parameters that you have to keep in mind while you are doing the electrospinning. Then types of charging system in electrospinning, like I was saying, that what kind of charging system you can have. So here you can see that the spinneret charging system, you can see the collector that is grounded, that is collector is not having any charge. You're applying a voltage to the spinneret, that is charged needle, and your collector. But since your collector is grounded, your collector is becoming neutral, and your polymer solution is extruded, and it comes to this neutral place. And another is a collector charging system, where you can see that your needle is grounded. You're applying a high voltage between your spinneret and the collector. Your collector is charged, but it is opposite charge to the polymer solution charge. Then only your polymer solution will come down to the collector. Understood? Different kinds of charging system that could be there in electrospinning. Any questions? Okay, so moving on, we have another very important kind of nanofiber fabrication. So you can do normal nanofiber fabrication, and you can do a core shell nanofiber fabrication. So this is also very important because your core will be made of one polymer solution, and your shell will be made of another polymer solution. So you can have like a hydrophilic core and a hydrophobic sheath, so that and you can load different kinds of drugs. So in the core, if it is hydrophilic, you can load hydrophilic drugs in your core nanofiber, and in the shell, if it is hydrophobic, you can load hydrophobic drugs there, and then you can do drug delivery. Okay, so this core shell nanofiber is also very important. So for this, what happens, instead of one spinneret, you have two, and they are both attached to each other. You can see here that the setup, that this is the main solution which is being ejected, which is the sheath, and you're adding the core solution. So it is mixed in such a way so that your core solution is inside, core polymer is inside, and the shell is the sheet solution is outside, and then you are collecting it. And this cross section, when you are doing SEM, then you will see cross section. If you do a cross section imaging of your nanofibers, you will distinctly see two layers in your nanofibers. If you do not form a core shell nanofiber, you are only forming nanofibers, then you will see only one layer. But when you are forming core shell nanofiber will give you distinct two layers, and you can measure diameter of your core and sheath separately. Okay, so this completes the electrospinning. Any questions? Any other questions regarding electrospinning? Any questions? Okay. So we will be moving on to 3D bioprinting. So 3D bioprinting is also a new wave in which a lot of researchers and scientists they are working currently. So what is bioprinting? Bioprinting is basically the layer by layer deposition of cells to create 3D tissue that closely resembles native tissue in form and function from basic biological building blocks. So our biological building blocks are basically what? Protein, like nucleic acids, proteins, peptides. So you can use all of those for 3D bioprinting. So here you can see you can also use cells for 3D bioprinting. So 3D bioprinting is layer by layer. Layer by layer, you will deposit cells to create a 3D tissue. So mostly now currently 3D, I think I mentioned it before also, that 3D bioprinting currently mostly it is used for making skin, because skin is the easiest organ to make for now, and easiest to graft also. So I think I've mentioned this in previous class, that how you can why do we need to 3D bioprint? Why we are 3D bioprinting organs? Can anyone tell me why we need to 3D bioprint organs? The need for 3D bioprinting.
For someone who has actually lost a part of ear, like for example, soldiers who have lost part of ear or
Yeah.
nose
So
by
basically,
bullet injuries.
yeah, bullet injuries. So any kind of injuries or body part you have lost, for that you can use it. And organ, that is basically ear or something. But if it is internal organ, then basically for organ transplant, because there is a high organ transplantation demand. Like the list is bigger compared to the organs available for transplanting. So to meet that demand, mainly this 3D bioprinting technique is very useful. You can 3D print organs, and what you will be doing is that, suppose you have an organ and you have a patient. The patient is waiting for a long time to get a organ transplant, but organ is available. When you checked it, you saw that that organ tissue is not compatible with the patient, so you cannot put that organ in the patient. If you do, the patient will die. It will reject the organ, host graft rejection, and then the patient might die. So what happens is that there is that problem when you're doing 3D bioprinting. The biggest advantage of 3D bioprinting is you basically take cells from the patient itself. So you're taking cells from the patient, you're growing them into an organ, and then you're transplanting the organ back. So since you have taken cells from the patient, so the patient's immune system will not recognize it as foreign and will immediately accept the organ transplantation. So that is one biggest advantage of your 3D bioprinting, apart from solving the organ transplantation demand. Okay, so no host graft rejection. So what is the 3D bioprinting process? What you need to do? So suppose here you can see they have 3D printed a nose and an ear. So if you want to 3D print a nose and an ear, what you need to do? First you have to make a model of the ear or nose. So first you have to make a model. So to successfully create bioprinted tissues, it is necessary to generate the printing paths. So you have to provide a path to the 3D printer, that along which path should the printer print. So you and that path will be provided, and what and how you will print it, that path will be provided by your appropriate bio ink. So and then you will control the bioprinter and perform quality control after printing. So basically what you have to do is you have to previously you have studied about bio inks. You remember what bio ink you studied, which I also answered as a question, like what you can use that for. That was a bio ink for 3D printing. A bio ink you already studied in this course. We talked about it in last class. No, 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 not silicon. It's peptide ink. Peptide ink we were talking about. So that is also a type of bio ink which can be used for your which could be used for your 3D printing, 3D bioprinting. So what will you be doing in this 3D bioprinting process? Just to give an overview, first you have to make a CAD model. So basically you have a AutoCAD software in which you have to make a 3D model of your organ. Most difficult part, the more complex your organ, the more difficult it is to make the model. So you have to make a 3D model. After that you have to save it as an STL file. You will get a STL file. Then you have to put that STL file in a slicing software like ZSuit or here Idea Maker. You put it in a slicing software. So what the slicing software will do is that it will take your 3D model and it will slice it into layers. As you can see here, it has been sliced into layers. Then why this slicing is needed? Because your 3D printer will print each sliced layer to print your 3D organ. Okay, so then your 3D printer will print each sliced layer, that is layer by layer it will print, and then your 3D object will be printed. So this is this here shown is a random 3D object, but you can do it in the same way for your 3D organ printing also. You have to make a 3D model, save the STL file, then slice it using a slicing software. You will get sliced layers. Then you will be using a bio ink. You have to decide on what kind of bio ink you will be using. Different kinds of bio inks are available depending on your application, depending on the organ you are printing. You will be using the bio ink, and then you will get your 3D printed organ. So generating the printing parts. So first is how you will generate the printing parts. I said you have to create the 3D model. So from where will you get the 3D model? Here usually what you do is you get the 3D model from medical imaging like computerized tomography or MRI, magnetic resonance imaging. So you will get this in decom format. So the correct anatomical shape of the desired tissue construct is achieved by representing clinical imaging CT or MRI data as a computer 3D model. So basically your STL, this STL file is important. This STL file format as an intermediate between model and print path generation. So you will get the first 3D model from your medical imaging, then you have to convert. You use this to make a 3D CAD model, which will be your STL file. So this is the first step of your 3D bioprinting. So creating a 3D model. After that, what you will do? After that, you will do is slicing. So in this slicing process, you can see that whenever you will give a model to print, the model will not be printed like this, like a simple cone. It will be printed slowly, layer by layer deposition it will do. Anybody has seen how a 3D printer works? Have you ever seen a 3D printer, how it works? Ever seen a 3D printer? Yeah. So basically, if you have seen a plastic one, the organ printing one will also work in the same way. So if the plastic one will printing layer by layer, right? So your organ will also be printed layer by layer. Yeah, from the ground up, correct. So from the bottom up, it will be making your 3D structure. So if you're printing from the bottom up, so you need, like I said, you need to slice it into layers. So suppose you have skin, or then you have to slice it into layers so that the skin is printed layer by layer. So from the bottom to the up, it will print your organ. So for this you need to slice. So in a process analogous to histological sectioning, that is like microtome, you ultra microtome you use to slice or make sections. So like that you will be making sections of your 3D model. Then printing parts are created by slicing this STL model into layers and creating bioprinter tool paths that trace out the perimeter and interior features of each slice. So basically your bioprinter tool paths will be created, and after slicing it will be utilizing every interior detail, outside detail as well as interior feature details also each slice will be having. So that is how it will be forming, it will be mimicking the entire organ. So imagine how difficult it will be to make a 3D model of a complex organ, because the more complex organ, the more intricate details will be there in the inside, more vasculation and all. So like I think I mentioned this also in a previous class, that vasculation is very difficult to do in 3D bioprinting. That is why till date nobody has successfully, as of yet, not successfully made any 3D model of any vasculated organ. 3D modeling of vasculated organs are very, very difficult. They have made maybe, but it, like maybe they've made a heart, but it will not beat. So imagine if you're making a heart, you need to make so much vasculations, and also it should be elastic enough to beat. So you will make a slice and then slice layer by layer from bottom up, it will start printing. So next step for printing will be selecting the appropriate bio ink. So you have to select the appropriate bio ink. What kind of bio ink you will use for 3D printing? So the bio ink is the bioprintable material consisting of living cells and biomaterials that resemble the ECM to support cells. So not only living cells, if you're using cells, the cells, we know mammalian cells, they need to adhere to grow, and to adhere, and they need certain factors for growth. All those adhering and factors will be provided by ECM, extracellular matrix, which will support your cells. So without biomaterials that will resemble the ECM, you cannot make a bio ink. So if you're using living cells, if your bio ink is having living cells, then you also need to add biomaterials which will form ECM, that is a scaffold. An ideal bio ink should possess proper mechanical, rheological, and biological properties of the target tissues. So only if you can make, so imagine you have to make making this bio ink is the most difficult part of your 3D printing process. Printing will be very easy, you just feed your data into the machine and machine will print it, but generating the bio ink is the most difficult thing, because the bio ink should have all materials which will mimic the mechanical, rheological, and biological properties of the target tissue. Then only you can successfully make a organ. So here you can see some example of some bio ink, like you can use polymers plus bioactive inorganic fillers plus cells. All of this will be 3D bioprinted, and then what you can do is application will be, you can form 3D print bone, you can do osteochondral repair, you can do vascularization, which is very difficult. So soft tissue engineering and drug delivery. So all of these things you can do by 3D bioprinting. So there are different classifications of bioink. First one is a scaffold based bioinks. So it consists of cells dispersed within biomaterials that help to create a conducive environment for cell proliferation as well as providing structural support. So basically scaffold based bioinks is, the scaffold will be acting like your extracellular matrix, which will create the environment for cell proliferation, and will also give structural support to your cells. So that is the scaffold based bioinks. And another bioink could be there, which is scaffold free bioinks. So these scaffold free bioinks are cells are bioprinted without a supporting hydrogel, and therefore cells are loaded in high concentrations, which then deposit their own ECM. So basically, well, for the scaffold free bioinks, these cells, they do not have a matrix on which they can grow. So you will load a high concentrations of these cells, you will deposit a high concentration of these cells in the 3D bioprinter, and the cells themselves will then form their own extracellular matrix. So mostly scaffold based bioinks are used. So for scaffold based bioinks, the types of bioinks that are used is hydrogel, which could be natural, like including collagen, fibrin, chitosan, and alginate, or it could be synthetic, like including methacrylated gelatin, fluoronic, and polyethylene glycol. Or you can make a hybrid of natural as well as synthetic hydrogels. Decellularized matrix components obtained by chopping tissue. One second. Okay. So decellularized matrix components obtained by chopping tissue into small fragments, lysing the cells and extracting the remaining ECM. So these can also be used as bioink. Okay, you can, because part of the bioink which will form the scaffold. So you can decellularize matrix component, and by chopping tissue into small fragments, you can lyse the cells and extract the remaining ECM, and basically use them for as a scaffold in your bioink. So these are the scaffold forming elements of your scaffold based bioinks. So another example is microcarriers. This is also very important. What you have is you have a carrier system in which your cells will be loaded, and then those cells will go and be printed on your scaffold. So microcarriers have recently been used in bioprinting to increase the cell density in bioinks. They are porous particles designed to promote cell attachment, survival, and expansion. So here you can see a picture of microcarriers. You can see that it's a sphere which is porous. So it will basically promote cell attachment, survival, and expansion, and it will deliver more number of cells for growing. So apart from that, you can also see other kind of scaffolding that can be done. So like microcarriers is one of them. Porous scaffolds you can use, hydrogels you can use, and fiber scaffolds you can use. So fiber scaffolds, just now we were talking about electrospinning. So fiber scaffolds will come through by electrospinning. Porous scaffolds will come by that self-assembly, and then drying, lyophilizing. That will form your porous scaffolds. Microcarriers you have to form in a different way, and hydrogels can be formed in different kinds of ways. So there are different techniques to form hydrogels. So consideration for scaffold selection is basically effects on taste, nutrition, and food safety, ability to facilitate oxygen, nutrient, and waste transport, cost, and scalability. So if you're 3D printing an organ, the cost should not be too high, and the scale, you can scale it up in industrial level, then only it will be effective. If the cost is too high, then a person who is waiting for an organ transplant cannot afford it. So you have to use materials which will be cost effective, so that the 3D printed organ is cheap. If your 3D printed organ is very expensive and a large sum of money is asked from a poor person for an organ transplant, then it is useless. So it should be cost effective. So another important part of your bioink is cell source. Apart from your scaffold, which will attach your cells and help promote cell growth, your cell source is important. So the biggest cell source for bioink should be autologous and patient specific. So these are the main two requirements for the cell component of the bioink, that it should be autologous and patient specific. So for that, what you do is you take stem cells from the patient. You know that stem cells, if you give different kinds of signals to stem cells, they will form different kinds, they will mature into different kinds of cells. So stem cells have that property. So that is why stem cells could be isolated from patients, and then they could be used as bioink, and depending on the type of signal you give to the stem cells, they will mature into different kinds of cells. So that will be your cell source. So, stem cells in 3D bioprinting. Stem cells have the properties of self-renewal and potency, representing an unlimited cell source for 3D bioprinting and regenerative medicine. However, autologous adult stem cells have to be obtained invasively through bone marrow harvesting, adipose tissue extraction by liposuction, or least invasively using blood apheresis. So, blood apheresis is basically, it is a instrument, it is a technique in which you use an instrument to take out stem cells from blood. Stem cells are other components from blood. Okay, so that it's a technique, blood apheresis. So that is the reason. So you have already been given the stem cells have the property of self renewal and potency. So it could be an unlimited source for 3D bioprinting. But if you have to use it, if you have to use adult stem cells, then you have to harvest it from bone marrow. So that's a very invasive technique. So that is non-negotiable, that if you have to take out adult stem cells, then you have to harvest invasively through bone marrow or by liposuction or by blood apheresis. So how did this idea to use stem cells come? Is in 2006 with the discovery of human-induced pluripotent stem cells, patient-specific stem cell lines can now be created from mature cell types such as peripheral blood mononuclear cells by venipuncture or dermal skin fibroblasts by skin biopsy. So this ability to reprogram patient-specific cells also allows for the creation of stem cells containing heritable mutations which can then be bioprinted and studied. So basically what happens is that you have to take patient specific cells and then reprogram it to form stem cells. So what are the stem cells in 3D bioprinting is, you can see that from the bone marrow you have collected bone marrow derived mesenchymal stem cells. So these are your adult stem cells. Or from skin you can take fibroblasts. You can do now you if you're taking fibroblasts, you have to make them into stem cells. So what you will do, you will viral reprogram it. You're using a virus to reprogram it to cause some mutations in this fibroblast so that they become induced pluripotent stem cells. Or you can get stem cells, embryonic stem cells directly from the blastocyst. So these are different ways you can collect stem cells from an adult human. So this has the potential to improve current understanding of disease mechanisms and phenotypic variability while minimizing rejection when transplanted back into the host for purposes of tissue regeneration. So I told you the biggest advantage of 3D organ bioprinting is that you take the cells from your patient themselves. So if you're taking patient cells and then whether you're reprogramming it or directly using the stem cells for growth, it is, since it is directly from your patient, it will not it will minimize the risk of rejection when you transplant it back. That is, there will be no host graft rejection. So this is an overview of how the 3D bioprinting happens. Basically, from the patients, you will take biopsy, that is, you will isolate cells. Then you will grow the cells, cell expansion. Using those cells and the scaffold material, you will form a bioink. Then you will use the bioink to you will use the bioink. You will make a 3D model of your organ, slice it, then use your bioink, feed your 3D printer with your bioink as well as the model, sliced model, and it will 3D print it. You will give maturogens to grow your organ to into a final mature form and then transplant it back to your patient. So this is an entire overview of how 3D bioprinting or 3D organ bioprinting is done and utilized. Application. Okay, so in order to start bioprint, so till now we talked about bioink generation. That was the first few steps for bioprinting. Second last actually step is bioprinting. So what you will do in bioprinting? So this was the first step. Cells you have taken, polymers or crosslinkers you have taken to form the bioink. After you are forming the bioink, you are using the bioink using different techniques. So what are the techniques? One is extrusion based bioprinting, one is inject based bioprinting, and another is laser assisted bioprinting. Okay, three kind of techniques you can use to bioprint, and then it will form an organ. You will check it first in vitro disease model, then do a drug screening, or you can use for tissue engineering. So this is how you start to bioprint using these three kinds of bioprinters. So you might have already studied about these three kinds of bioprinters. First is an inject 3D bioprinter. So this can be of two types. First is a thermal type, another is a piezoelectric type. Thermal type is basically you're heating your bio ink. There's a heater here which will heat your bio ink and then inject, means drop by drop it will inject your bio ink. In the piezoelectric one is you instead of a heater you have a piezoelectric actuator. So this piezoelectric actuator, what they will do is it will put a mechanical pressure on your bio ink, which will be converted into electrostatic charge in your bio ink, and then it will be printed. Okay, so bioink in the Inject 3D bioprinter, what happens? Bioink is stored in the ink cartridge, which is connected to a printer head and acts as the source during the electronically controlled printing process. So during printing, the printer heads are squeezed by a thermal or piezoelectric actuator to generate droplets of a controllable size. So you will generate droplets and you can control the size of these droplets. So this is basically your Inject 3D bioprinting. So there are some certain advantages of Inject bioprinting, that is low cost due to similar structure with commercial printers, and it has a very high printing speed and relatively high cell viability, usually from 80% to 90%. Okay. Then you have the second one is extrusion or micro extrusion based bioprinting. So this can be of three types, as you can see in this picture. One is you're using a piston to push the cells. Another is you're using air pressure to push your bio ink through the nozzle for printing. Another is using a rotary screw. So there will be a valve, you're rotating a screw and then you're applying pressure to in extruded through the nozzle for bioprinting. So extrusion printing is a modification of inject printing. So in order to print the viscous materials, inject printers cannot deposit. Extrusion printing uses either an air force pump, piston or a mechanical screw plunger to dispense bioinks. So this is your piston, this is your air force pump, and this is the mechanical screw plunger to dispense bioinks. So when you will be using extrusion based bioprints, when you have to print viscous materials which inject printers cannot deposit, then you will be using your extrusion based bioprinting. Last one is your laser assisted bioprinting. In this, what happens is you have a focused laser pulse is applied to stimulate a small area of the absorbing layer. This laser pulse vaporizes a portion of the donor layer, creating a high pressure bubble at the interface of the bioink layer and propelling the suspended bioink. So you can see here you are applying a laser and then you have a gold absorbing layer and you have the bioink. So this gold absorbing layer will be stimulated and it will vaporize a part of this gold absorbing layer. It will vaporize it and your bio ink droplet, printed droplet, will drop into the receiving substrate. So here you can see a mouse model in which there is a receiving substrate and your bio ink will vaporize and drop here onto the receiving substrate. So this is your laser assisted bioprinting. So there are different applications of 3D bioprinting, especially 3D bioprinting in healthcare is one is organ regeneration. You can make organs. One is bone tissue engineering, that is you can reform bones or you can repair damaged bones. Then you can do drug development using 3D bioprinting. You can do skin tissue engineering. I said that whenever you have patients with very severe burns, like third-degree burns, so you can do skin tissue engineering. You can take skin tissue cells from other parts of that patient's body. Then you can grow them and you can graft it to reconstruct that person's face. or any other body part which is severely burned. So skin tissue engineering. So this is what mostly is used currently, and you can also develop certain medical devices using your 3D bioprinting. So this is all for today. Thank you. So you have any questions? Okay, one second. Uh, yes. On uptaking bioprinting, what is the chances of grafting? Could you make your question a little bit more clear?
Sure, ma'am.
Yeah.
Ma'am, on taking bioprinting, what is the chances of graft rejection, ma'am?
Oh, graft rejection is very low. Like I was saying, that for 3D printing, what you're doing is you're taking cells from the patient. So what you will be doing is, like I was talking about, mostly what you do is you take stem cells, because stem cells you can form different kinds of cells from stem cells. We know that it has self renewal property. It has the capability of forming different kinds of cells. So stem cells are your main kinds of cells you can use for 3D printing organs. So for that you will be collecting from the patient. So what you do is you do a biopsy. Usually the biopsy is invasive. I was talking about that if you collect adult stem cells, then you have to collect it from the bone marrow, which is very invasive technique. So from the bone marrow you will be collecting bone marrow stem cells. Then you will be using those stem cells as bio ink to grow a specific organ. Depending on the type of organ, you will put factors so that it matures into that organ. The stem cells reprogram and form those cells for that organ, and then you will put it back in the host. So since you're taking the cells from the host and grafting it back in the host, so there will be very less chances of host graft rejection, almost negligible.
Okay, ma'am.
Yeah. So this is what I was saying is the problem with normal organ transplant. You have to find compatibility between the donor as well as the receiver. Then only there will be no host graft rejection. But this compatibility issue does not is not a problem in 3D bioprinting, because cells are taken from the patient. Any other question? Any other questions regarding material that have been taught? Like, do you have any questions regarding anything that has been taught in the last 4 weeks lecture? Anything you did not understand?
Ma'am,
Yes.
um, compared to bioprinting, transplanting is also right, ma'am. But it may have graft rejection, but financially it is okay, right, ma'am?
Financially, if you think about it, the problem, like the reason people came up with this 3D bioprinting technique, because like I was saying, the patient list is very long, and the number of organs that are being donated on a daily regular basis is very less. So that list of patients that you have, yeah, large scale production, yes, right. So basically the list is very long. So according to the list, they will go the first person on the list. If an organ comes, that person gets priority even if somebody else is dying. Okay, so that is one problem, that too much of demand and very less you have. Because organ donation, you have to, a person has to donate an organ, has to agree to donate organ when they die. Then only you will get the organ as transplanted. Then only you can transplant that organ. Otherwise, yeah, otherwise, yes, correct, a lot of people die for not getting organ transplant. And the main problem is that mainly one is organs are very less, and then again, how many people do you hear that they agree to donate organs? You cannot harvest. Every day people are dying, but you cannot harvest organs if they have never said that they want to give their organs when they die. That is also a problem. So there are ethical issues on that. So that person's family members can come and claim that you have taken my father's or mother's organ without informing me. That's illegal. Sometimes people do that. So, firstly, very less number of people sign up for donating organs. So, very less organs are available for donating and transplantation. And but the list for people requiring organ transplantation is very big. So that is why we are doing this. And since the list is very big and the demand is more and supply is less, you can understand how much they monetize it, how much they will be asking for one organ. So if you can make organs readily available, like if you can 3D print organs and you can make them readily available using some uh, uh, materials which are cheap, not that much expensive, then you can make organs available to a large number of people who need it at a very low cost. Then again, it depends on the people who are marketing. If people think that we are printing organs, 3D printing organs, we want to charge a high rate for it. So it depends on the people and their mentality. That is also there. But let's not go into that. Ultimately, your aim as a researcher is to make something cheap so that it can be marketed, so that even a poor person can come and afford it. That should be your aim.
Thank you, ma'am.
Yeah. Welcome. Any other question? Anything else? No problem regarding anything regarding the course? Have you guys all submitted your weekly assignments? All assignments submitted? Because I think this ends the course. This is the last week for the course. You will directly be having your exams. Okay, one more you have to submit. Okay. So okay, okay, fine. So one more assignment is remaining, and then after that you are done with this course. And so how did you enjoy? Did you enjoy this course? Did you learn a lot? Anything different you learned from this course? Okay. So you learned something new. So will you be willing to implement it in the future? Are you guys planning to work in nano? Do some synthesis, make some material in nano? Okay, very good. So we are glad that this course could be helpful for your knowledge and you can use it for your future research purposes. So, any other queries or questions you have, even if we do not have any more live sessions, you are always welcome to like send questions. We will try to address them till your exams. Oh, PPT, I think I have sent a mail. Did you not receive my mail? When I sent you an invitation for this live session, I sent a G Drive link. That link is having all the three PPTs, and this PPT I will upload right now. After the session ends, I will immediately upload it in that drive. So, in that drive link, you will get my presentations. Okay. Just a second. 1 second. Okay, 1 second. I will giving you the drive link. Okay, that's the drive link. I have pinned the drive link. You can see in the chat. If you open this drive link, please one of you open and tell me that you can see presentations and download. You do not need permission. I think I've given access to anyone with link. Please do it and confirm one time that you can see.
Yes, ma'am, it's opening.
Okay, so I have uploaded 3 presentations. Today's presentation also I will upload in the same drive link, and you can find like this is just for I think I mentioned it before that my presentations are not part of your exam syllabus. It's only for your information, it's only for your research purposes. Since this was supposed to be a live session for discussing problem solving session, but since I do not have your previous questions available, so it was very difficult for me to discuss previous year's questions. So that is why I thought of doing some sessions where I will be providing some extra information for your research purposes. And if you want to know more about each topic, then you can see certain YouTube videos regarding the same, or you can read up on your own. But basically, this was to give you an overview that this is how it is done, and how you can use techniques for different kinds of nanoparticle synthesis, how you can use characterization, what kind of characterization you will use for your nanoparticles. So these are like very important. So what kind of nanoparticles you will use for what kind of characterization. So whenever you're synthesizing a nanoparticle, the first thing that should come to mind is what kind of characterizations are applicable for this nanoparticle or nanofiber. So one of the characterization technique that I did not mention, which you should do for electrospinning, that is nanofibers, that is TGA, gravimetric analysis, TGA. So basically what you do is you take a nanofiber, you heat it at very high temperatures. So at different temperatures, it will be melting. So it will give you how stable your nanofiber is at what temperature and at what temperature. So TGA I did not discuss. That is important for your nanofiber characterization. And another one is XRD, X-ray diffraction. That also I did not discuss because it is too much of physics. I don't know how much you will understand. It talks about Bravais lattices and a lot of other things. So XRD will be a little bit difficult to understand. So basically XRD helps us understanding the crystallinity. You remember the SAID pattern we talked about in TEM? TEM we have a SAID pattern, selected area diffraction pattern. Selected area electron diffraction pattern, SAID pattern. So that SAID pattern, that same kind of pattern is basically, it depends on whether your material is crystalline or amorphous. You'll get a SAID pattern accordingly. Polycrystalline, crystalline and amorphous. So that SAID pattern you will get in TEM, but there in each pattern you will get a plane. That plane indexing is done in XRD. What kind of planes you have, that is done in XRD. So if you want to know about XRD and TGA, you can read up by yourself. I just mentioned them so that you know that these are also other techniques which I did not talk about. Apart from that, I think I talked about most of the characterization technique like FTIR. Raman spectroscopy I did not talk about. Raman spectroscopy also sometimes you use, not all times, and not for all nanomaterials. For some nanomaterials you have to use Raman spectroscopy. So FTM mostly you use SEM, TEM, UV visible, FTIR, EDAX. These are most commonly used. So apart from that, I mentioned XRD and TG as well. Fluorescence, photoluminescence spectroscopy also I think I've covered in brief, characterization technique. So that completes most of it. Yeah. whatever characterization techniques you can use for your nanoparticle synthesis. What kind of nanoparticle, what kind of properties it has, and oh yes, DLS, zeta sizer instrument. So any confusion regarding any characterization technique? What cuvettes to use? What kind of cuvettes you will use? Everything is clear? UV visible, what kind of cuvette you will use? What kind of cuvette you will use for DLS? What kind of cuvette you will use for PL? Any confusion in any of these techniques? I'm not sure if you guys were there in the first class or not, because I discussed all of this in the first live session. 2-volt cuvette for UV visible, 4-volt cuvettes for DLS and PL spectroscopy, out of which quartz cuvette for UV and PL spectroscopy, and photoluminescence and DLS you will use polystyrene latex, so no organic solvents. If you use organic solvents, your cuvette will be destroyed because it's made of polystyrene latex. Okay, so these are all certain topics we talked about. So that was just to give you an overview. So if you have no more queries or no more questions, so we will be ending today's session, and this was the last session for this course, last live session for this course. So thank you everyone for joining. It was a pleasure interacting with you, and I hope you guys learned a lot in this session, in these sessions, as well as in this course. And I hope that you utilize all this information in the future for your research work. So thank you so much for joining today as well as the other days, and thank you for interacting with me. It was a pleasure to talk with all of you. So I wish you well for your future work. So thank you. So you may leave one by one. Thank you. Yeah, welcome. Thank you.